In today's lesson, we are going to be looking at negative and zero exponents. So just as a little bit of a warm-up, a binary lock consists of several switches that can either be on or off. So the first question involving these locks or switches, if a safe uses one switch, how many possible combinations are there, and what are they? So for example, work through the first one. If there's one switch, for example, just this switch here, what possible combinations are there? Well, it's either on or off. So it's on or off. So there are two possible options. Now, what if there are two switches? So what if we had these two side by side? Well, we could have, and I'm going to use different symbols. I'm going to say up and down, just because on and off are both O's. So I could have up and up. I could have down and down. I could have the first one up, the second one down, the first one down, the second one up. So I have four possible situations or combinations of the switches. Now, what if I had three switches? Right, so I had three, right? I had an up, a down, an up, a down, up, and a down, or on and off, on and off, on and off. How many different combinations could I have? Well, I could have up, 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 down, 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 up, down, 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 up, down, up, down, down, up. And I think there's one more. Down, up, down. I think that is it. And I only think that's it because I kind of know how many there are already from doing this before. But I think if you go through, you won't find any other combinations. So that was a simple one. That was with 1, 2, or 3 switches. Now, a 64-bit encryption, something that you might see or hear of similar to in emails or banking transactions, there's a 64-bit encryption, and essentially it would be something like 64 switches. Now, how many possible combinations are there if we have 64 switches? So 64 switches with this up, down, up, down, up, down, up, down, and so on. Probably going to be pretty impossible, or not impossible, but very, very, very time consuming to go through and do this for every for all 64, right? I'm not going to write out up, down, so on, all the way through and go through and think of all the different combinations. But let's go back and see if there's an easier way to figure it out. So if I go back and look at A, there are 2 ways. If I look at B, there are 4 ways. If I look at C, there are 8 ways. So I have 1 gives me 2, 2 switches gives me 4, 3 gives me 8. Is there a pattern there? And there is a pattern, and actually what's happening is we're multiplying by 2 every time. 2 times 1, 2 times 2, 2 times 2 times 2 for the third one. So I could actually do 2 to the power of 64, right? The 64 because there's 64 switches. And I would actually get, rather than going and doing this by hand, I would get 1.8446744407 times 10 to the power of 19. So this is basically a very, very, very large number. And we're going to be looking at some exponents today. So this is kind of just a warm-up into that. We're going to look at this type of exponent, or this form or use of exponents, what we call scientific notation. Another similar warm-up, how many times would you have to fold a piece of paper to get to the moon? So the information that we're given, from the Earth to the moon, it's 384,400 kilometers, and the one piece of paper is 0.5 millimeters thick. So 0.5 millimeters thick means it's 0.005 centimeters thick. Divide that by 100. 0.00005 meters thick. And divide that by 1,000. 0.12345 kilometers thick. So using that information, can you figure out how many times we would have to fold a piece of paper in half to get to the moon? And to kind of help you out, one fold, it now becomes 0.1 millimeters thick. Two folds would be 0.2 millimeters thick. Three folds, 0.4 millimeters thick. So think about similar to what we were doing in the last warm-up in terms of doubling or multiplying by 2 every time. Think about what you were doing here and see if you can work out how many times you would have to fold a piece of paper to get to the moon. So all of those warm-ups were dealing with exponents, right? You should be familiar with exponents. If we're doing order of operations before, we have dealt with exponents. This is an example of what we call a power, right? So the entire thing here is what we call a power. And a power consists of two parts. One, we have our exponent, and we have our base. So the exponential form is exactly what we see here, where the power, it's 5 to the power of 6. Now the expanded form is what this actually represents. And this actually represents 5 times 5 times 5 times 5 times 5 times 5. So this actually represents 5 times itself 6 times, or the base multiplied by itself however many times the exponent tells us. So if we punch this into our calculator, either way we should get the same answer, same representation, or same value, just represented a different way, 15,625. So we should be familiar with exponents, but what we're going to be doing now is looking at different types of exponents and some applications of them. And the first one is the negative exponent rule. So we haven't really dealt with negative exponents too much, but we could have a negative exponent. And what that means is if the base is raised to a negative exponent, it is equal to the reciprocal of the base raised to the positive of the exponent. So a lot of fancy words there, but essentially all that's saying is if I have a to the power of negative n, that's the same as the reciprocal, so the flipped version, so 1 over a to the power of positive n. Or you could say the reciprocal, so I flip it, it's now raised to a positive exponent. That positive exponent applies to both parts, but because 1 to the power of anything is 1, we can just say it's 1 over a to the power of n. So for example, 2 to the power of negative 3, the reciprocal would be 1 over 2, where we flip our base. Flip here. And we now raise it to the positive exponent. That 3 applies to both parts. So 1 to the power of 3 over 2 to the power of 3. 1 times 1 times 1 is still 1. 2 to the power of 3, 2 times 2 times 2 is the same as 1 over 8. I could skip and go from here to here if we wanted to, right? This is just showing the two different forms, right? Exponential and expanded. The zero exponent rule is probably the easiest one, or the easiest rule that we're going to learn. And that is just, if a base is raised to an exponent of 0, the result is 1. So a to the power of 0 equals 1. So for example, 4 to the power of 0 is 1. It doesn't matter what the base is, whether it's a letter, whether it's a number. If it's raised to the power of 0, it equals 1. So let's go through some examples. Let's evaluate the following. So 5 to the power of -1. Okay, I have a negative exponent. I need to write the reciprocal, so I'm going to flip my base, 1 over 5, and that's going to now be raised to the power of the positive exponent, 1. That 1 applies to both parts. I get 1 over 1 to the power of 1, which is 1, over 5 to the power of 1, which is just 5. B is similar. I have to write the reciprocal of the base. So instead of 3, it's 1 over 3 to now a positive 4. So when I flip the base, I change the sign on the exponent to positive. That power of 4 applies to both parts. 1 to the power of 4 doesn't really change anything. 3 to the power of 4. 1 to the power of 4 is 1. 3 to the power of 4 is 3 times 3 times 3 times 3. Equals, and again, I don't need to write that expanded form. I'm just doing it to help us understand a little bit of how we're getting this bottom value. 3 to the power of 4 is 81. So 3 to the power of -4 simplifies to 1 over 81. Now, you could enter that into your calculator and you would probably get a decimal. Depending on the type of calculator you have, it might give you a decimal, it might give you the fraction. In our case, in our examples, in our practice, in our assessments, it's most likely going to ask for the answer as a fraction. So make sure you know how to convert it, flip it, apply the exponent, and evaluate it without turning it into a decimal. Then the last one, 10 to the power of 0. So our rule, anything to the power of 0 is equal to 1. We have 3 more examples. I'm going to go through the first one just because it's a negative exponent or a negative base, and then I'm going to let you try the last 2 on your own. So -6 raised to the power of -2. Negative exponent means we flip our base, right, the reciprocal. So 1 over -6 raised to now the power of +2. So this becomes 1 to the power of 2 over -6 to the power of 2. One thing to keep in mind, we have the brackets. So we don't want to forget the brackets. And the reason we don't want to forget the brackets is because our calculator may not take the negative and apply it with the exponent. So this actually works out to 1 over -6 times -6, because it's raised to the power of 2. But depending on our calculator, if we don't put that negative there, or those brackets there, it may think that we're doing 6 times 6 and just the entire thing is negative. But when we multiply a negative by itself, we should get a positive. So just make sure you're using the brackets when you're applying these exponents or when you're typing it into your calculator. So try to do E and F on your own, and we'll come back with the answers. So coming back for the first one, or for E, we flip the base because of the negative exponent. It becomes 1 over -4 to the power of 3. That power of 3 applies to both parts. -4 to the power of 3 means -4 times itself 3 times, which means in this case I will get a negative number because a negative times a negative times a negative is a negative. So I have -64. And then for F, Negative 250 to the power of 0 is 1. Now, with negative and positive exponents, we can work with scientific notation. And scientific notation is a method used to express very large or very small numbers that are very difficult to say and write. So it makes these numbers more manageable. So for example, the mass of the Earth is approximately 5, 9, 7, 6, and then 3, 6, 9, 12, 15, 18, 21 zeros, and then kilograms. So it's a very large number. Similar to the diameter of an electron, it's a very small number. So if I were to try to say that out loud, I don't know what that number is. I don't know what the units or the placeholders are. Right? It's more than a billion. It's more than a trillion. I'm not too sure exactly what it is. So it's difficult to say. So that's where scientific notation can come in handy. And to write a number in scientific notation, if we're taking a very large or a very small number, we want to place the decimal to the right of the first non-digit or non-zero digit. So if I look at these two values in purple here, and I can see where I've placed the decimal, it is after the first non-zero digit. And then they're both multiplied by a power of 10. Right? The top one is 10 to the power of 6 because we're making a big number, and the bottom one is 10 to the power of negative 3 because we're making a small number. And we're going to look at how to do that. So example 2, we want to write each number in scientific notation. So in A, I have 13860000000. So in order to write this in scientific notation, first thing says we need to put the decimal after the first non-zero digit. In this case, the first one is 1. So 1.386. And I'm only going to write that many, I'm only going to write out the digits that are not 0. The next thing we're going to do is we need to multiply it by a power of 10. So we have to figure out, okay, how many tens do I need to multiply it by to get this value? And an easy way to figure that is to figure out how many times did I have to move my decimal place. Well, the decimal place originally was here at the end, and I moved it 1, 2, 3, 4, 5, 6, 7, 8, 9. I moved it 9 spots. So that means the exponent will be 9 because I've moved my decimal place 9 places. This would actually work out to 1.386 times basically 1 followed by 9 zeros. And that would be, if I were to expand that, that would work out back to this. So this is what essentially we're doing, except we're just simplifying this, because rather than writing out this, what would this be, 1 billion, 1 trillion, yeah, 1 billion, right? I can simplify that to just 10 to the power of 9. So say there are 9 jumps. That's why we get the 9. For B, we're dealing with a small number, so the same idea. We still want to put the decimal after the first non-zero digit. So that would be after the 5. I'm going to multiply it by 10 raised to a power. And in this case, because I'm making a small number, it's going to actually be a negative exponent. And the same idea applies. The exponent is going to be how many times I move the decimal place. So 1, 2, 3, 4. That makes it an exponent of negative 4. So 4 jumps here, which means it's a negative 4. The reason it's a negative is because we're writing out, or it's a small number. So when we multiply by 10 to the power of negative 4, this is actually the same thing as saying 5.25 times 1 over 10 to the power of 4, or 10,000. So we're actually multiplying by a very small number, which would give us a small number in the end, which is what we want. So to compensate or to account for the fact that we're writing a large number, the 5.25, to make it small, we have to multiply by a decimal. We'll try one more. So again, the number after the first non-zero, so 7.5, we're going to multiply it by 10 raised to a power. In this case, the decimal would start here. I move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 jumps means the exponent is 11. So this, written in a simplified form, is 7.5 times 10 to the power of 11. If we want to rewrite the number in standard notation, if we want to see what does that actual value work out to, right, we're kind of reversing the pattern. So 2.5, so we're going to start with 2.5. The 6, remember the exponent tells me the number of jumps. So what I could do is I could actually multiply this out. 10 to the power 6 is 10 times 10 times 10 times 10 times 1, 2, 3, 4, 5, 6, and actually get a value. Depending on your calculator, you may not get the actual value. They may put it back into standard or scientific notation, but this is actually saying I'm moving it 6 times. I'm moving the decimal place 6 times, right? Because when I multiply by 10, I move up like a placeholder from the ones to the tens to the hundreds to the thousands and so on. So this would actually work out to, and a quick way to do it is to jump. So 1, 2, 3, 4, 5, 6. That's where my decimal is going to end up now at the end. And I'm going to place zeros in for my placeholder. So this actually works out to 25,000,000. When we have a negative, it's the same idea. Right? If I were to write this out in standard notation, right, 10 to the power of negative 4 is the same thing as saying 1 over 10,000. So 1.25 times 1 over 10,000, or 1.25 divided by 10,000. But again, that's not that easy to do, right? And your calculator may sometimes give you the value in scientific notation either way, even when you do that division. So we're going to do the same thing. The negative 4 is the number of jumps. But because it's a negative, I know I have to make a small number, so I'm actually going to jump to the left this time. So that means 1, 2, 3, 4. That's where my decimal is going to be. I'm going to put in zeros for placeholders, put a 0 at the front. So this actually simplifies to 0.000125. And that is my standard form. We'll do one last example. We're going to kind of do a quick way rather than showing the full expanded form. So 8.75. The 8 tells us the number of jumps. It's positive, so we're going to jump to the right. So 1, 2, 3, 4, 5, 6, 7, 8. That's where the decimal is going to go. In my expanded form or standard form, I'm going to fill in all the missing or empty spots with zeros as placeholders. So I have 8, 7, 5, 1, 2, 3, 4, 5, 6. 6 zeros. So that is my my standard form notation for this scientific notation. So just as a summary, if we're going from scientific to standard, kind of what we just did, the exponent tells you how many places to move the decimal point. Right? If it's a positive exponent, we move the decimal to the right. Negative exponent, we move the decimal to the left. If we're going from standard to scientific, we move the decimal to the right of the first non-zero digit, and the number of times you move the decimal determines the exponent. Moving the decimal to the right means the exponent should be a negative because it's a small number. Moving it to the left means the exponent should be positive because you're dealing with a large number, right? So it's flipped, it's opposite, right? When we're going from scientific to standard, if it's positive, we move to the right, negative to the left. In standard to scientific, we're moving the decimal to the right, means we're making a negative, or it should be a negative because we're making a small number larger. If we're moving the decimal to the left, the exponent should be positive because we're making a large number smaller. So it's kind of a reverse thinking. Yeah, it's just an application of some of our exponents. So again, the main thing is just understanding some of the rules for negative exponents, zero exponents, and how to do scientific notation.